Hi guys and welcome to Byochem. It's great to be back. I've got to start today with two really big, deepest apologies, and I've really got to say this big word here to the YouTubers because two reasons really. One, the lack of videos that I've made recently. I've just recovered from a serious strain of man flu, so I'm really sorry that I haven't been here. And two, the lack of joke at the end of last time. I can't believe it. I promised you two things here. I promised you funny hats, and I promised you joke, and I forgot the joke, and I'm really disgusted with myself. So today I've got two jokes, and I've got a special hat. So the joke from last time, which now is actually going to be amazing, is what did one stereoisomer say to the other stereoisomer? Hey mate, I can see you in the mirror. Oh come on, that's amazing! Oh, I will make you smile at some point. Okay, so some of you may notice that this is a different room to what uni was. This is actually my home, and that's because I've gone home because it's Christmas! That's probably enough for the singing Christmas carols. Right then, so let's actually get on with some work today. Today we're looking at acids and bases. I can't remember if I said that or not. Anyway, we're looking at acids and bases today. Okay, so we're going to start by looking at the three key definitions of acids and bases. So we're going to start with the Arrhenius definition, and the reason we start here is because it was the first definition of acids and bases. Okay, now, Arrhenius said, because Arrhenius was a man, that acids will ionize in water to give H+ ions, and bases will ionize in water to give OH- ions. That's perfectly true for a lot of acids and bases. Now, unfortunately, that only applies actually for aqueous acids and aqueous bases, so it doesn't cover the full range, and also doesn't cover this lovely molecule here. This is ammonia, and obviously does not ionize in water to give OH-. So we needed another definition for acids and bases. Now, this next definition came from two men working on acids and bases at the same time, but actually in two different places. They didn't actually work together, and that's Bronsted and Lowry. So it's a Bronsted-Lowry acid and base. Now they said that an acid will be a proton donor and a base a proton acceptor. Now that also applies again for the Arrhenius acids and the Arrhenius bases, but now includes those pesky ones that didn't work, such as ammonia. Ammonia now can act as a base because the nitrogen has a lone pair of electrons that can attack the proton to make ammonium ion, so you acting as a base. However, unlike the other definitions, the Bronsted-Lowry acid and base still didn't cover every acid and every base that there was. Now, if we look at the ammonium ion to show what I mean here, you can see that the nitrogen is donating a pair of electrons to the proton as a base. So you can say a base is an electron donor, and the proton is an electron acceptor as an acid. So an acid is an electron acceptor. Now you can use that as a general rule for all acids and bases, and this is called a Lewis acid and a Lewis base. Now you may say that I've just made this a lot more complicated than it needs to be, but there is an example actually that this doesn't apply, and I'm going to show you that right now. Okay, so this molecule here is an iron molecule with 6 coordinate bonds around it. So this is actually a ligand complex, or a ligand complex, depending on which teacher you had at A-level. And as you can see, the iron is accepting electrons from the OH2 molecule. But what does that mean? If you think about it, the iron molecule is accepting the electrons from the OH2 in the same way that the hydrogen was accepting the electrons from the NH3. So the iron here is acting as an acid, and all the other molecules acting as a base. Now this wouldn't work for the Bronsted-Lowry acid and base, or the Arrhenius acid and base, so this is why you have your third definition, your Lewis acid, and it works for all ligand complexes because both electrons in the covalent bond come from one species out of the two. Okay, so now we've looked at three definitions of acids and bases. I'd like to look at how you would quantify the strength of different acids and different bases. Now this happens differently between strength, so if you've got a strong acid or a strong base, you'll use one method, and if you've got a weak acid or a weak base, you use the other. Now I'm only going to use examples that use acids. I'm not actually going to look at bases, but the same things apply, and if you've got a bit of wits about you, then you'll realise what's going on. So we'll start actually with a strong acid, and that's because it's the most simple. Now a strong acid, represented here by just HA, will dissociate in water fully. I say dissociate because my text here dissociates fully to make A- ions, which is the other bit, and H3O+, which is what we call the oxonium ion. Now you can take the concentration of the oxonium ion, you can minus log it, and that will get you the pH. And then obviously you can use the pH on a pH scale to test how acidic or how basic a substance is. Okay, so the million-dollar question is now how do we look at weak acids and weak bases? Now, if I use my whiteboard again, you've basically got the same equation at the top. You're going from acid and you're dissociating to make your... That's my phone going off. Very unprofessional, I apologise. But if you notice, you're actually at equilibrium in the top one now. You're at equilibrium rather than your ions dissociating fully. They'll probably actually only dissociate a little amount. From that, we can use the rules of Kc, the equilibrium constant, to do products divided by reactants. But actually we can call it Ka, because we know it's an acid, and we actually ignore the water, because the water is on both sides, and it's more constant than it is anything else, so we can ignore it. Okay, so you've got products, then over reactants to make Ka, which is in mole DM -3. When you've got Ka, you can minus log that number, as we did H plus ions last time, to make pKa rather than pH. And just as pH, you can use pKa against other pKa values to test how acidic or how basic your compound is in that particular solution. Okay, so I'd like to stress that that isn't the full acids and bases topic that I'm about to go through this time. I'm going to put another acids and bases 2 up, and I'll be looking at buffers, titration curves, and indicators and how to choose them. So don't panic. If you've got any questions, please put them down here, or if you've got anything else that you want to talk about, or you think that I've missed, that's a big possibility, please tell me and I'll have a look at it. So, thank you very much. Okay, so as promised, I'm going to show you another crazy hat that I've got here. This is my wreath that I wear over Christmas. I made this outfit that I'm about to show you in a minute for a Grinch party that I had with my family, and I thought that because of missing my joke, I thought that YouTube social suicide was the way to go forward. So I'd like to leave you with a great snapshot of my amazing jumper that I made, well, with the help of my family. So have a great Christmas, everyone, and I will see you in the new year. So here you are. Here is my amazing jumper that says I love Xmas with my padded heart at the side. Ow, that was my knee! Ow.